Oh, okay, there it goes. All right, so yeah, today we're doing 4.4, which is concavity. And so the very first thing we're going to talk about is this. Well, here, let me first tell you, define concavity. So, let me start with kind of the informal definition, and then I'll talk about the formal definition. But basically, actually, hang on. For the informal one, I can only really draw a picture. So here, concave up is this one, right? If it, oh, sorry, I accidentally closed it. If it has a min, then it's going to be concave up, right? But then concave down, oops, is going to look like that. And so that's the informal definition, is just a picture. I'm not even really sure how to describe that in words. But the formal definition would be if the graph of f lies above all of its tangent lines on an interval, then f is concave up. Then f is concave up on that interval. And so, can you guys kind of see what I'm talking about here? So if I draw a curve that's concave up, and I start drawing all of the tangent lines to all of the points, do you guys see how it's sitting on top of each one of these tangent lines here? Oops, that was not actually a tangent line. But it's like above every tangent line that I could possibly draw to this curve. Do you guys see that? Does that make sense? Since there's not that many of you, yeah, I'm just gonna ask you guys type yes or no. And then again, if you don't want if you want to send a private message, you can. And then also, if you want to unmute yourself, you can, but just beware that it'll end up on YouTube. I'm sure not that many people are going to watch these though. I cannot figure out how to see who's part of the meeting right now. All right, only 4 people said yes, but I'm gonna move on anyway. Okay, and then yeah, concave down is kind of the opposite, right? So definition. If the graph of f lies below all of its tangent lines, then it's concave down. On an interval, then f is concave down on that interval. Okay, so are there any questions so far about concave up versus down? No. Oh, somebody left. No. Okay. So then what I'm going to show you right now is something called the concavity test. So I'm going to scroll up a little bit. Oh, here, let me draw a picture for this real quick. So concave down, yeah, if I draw all of the tangent lines, oops. Then yeah, it's gonna sit like below every tangent line that I could draw. And that one got a little messy. All right, but then yeah, so let's talk about the concavity test. So same way that there's like, last time we had talked about the increasing, decreasing test and the first derivative test and all of that stuff. And so, and that was basically, you use the first derivative to see when it's increasing, decreasing. You can use the first derivative to see when it has a min or a max. And so here, the concavity test basically says you can use the second derivative to determine where it's concave up or down, right? So the first thing, the first part of the concavity test is that if your second derivative is positive, so if your second derivative is greater than 0 for all x on some interval, then f is concave up on that interval. And we're going to draw a picture at the end of this that kind of shows you how all of the derivatives, or how f, f prime, and f double prime kind of connect to each other. But so then, yeah, f is concave up on that interval. And then, yeah, what do you think the second derivative has to be for it to be concave down? Yeah, negative or less than 0. Yeah, so if f double prime of x is less than 0 for all x on some interval, then f is concave down on that interval. Okay, before we do an example, there's one more definition I have to give you, but so far, does this all kind of make sense? Okay, cool. So then the next definition I have to give you. Also, if I start going too fast, just please let me know. I have no sense of when I'm going too fast anymore because I can't see you guys writing. But yeah, so if I scroll up or if I scroll down and I'm like, what you're working on, just kind of let me know. And remember, you can send private messages too. Okay, but yeah, so definition, a point P, actually, hang on, don't write that down. Let's change this a little bit, make this a little less formal. What I'm gonna say instead is just an inflection point. So that's what we're defining. Inflection point is where f changes concavity. Yes, exactly. And this is also just in case I go too fast or in case you have any questions later, it's always there. And then, so the notes will be on Blackboard, the videos will be on YouTube, but I don't want that to mean that you guys stop showing up to these Zoom meetings just because, oh, it's on YouTube. Because you still get something out of it when you're like actively participating, right? And then you get to ask me questions also. And so that's something I was going to talk about at the end, but I may as well talk about it now. Attendance. I'm going to start taking attendance at some point, and I'm not sure how it's going to factor into your grade, but I am going to be checking to see who's actually coming to these meetings and who's not. And so if you have a reason for not being able to join, let me know as soon as possible. But yeah, I'm going to get back to, are there any other questions about that? Okay, so let's do an example. But so yeah, like I was saying, basically with the second derivative, or with these inflection points, they're very similar to critical points, right? Except they're for the second derivative now. And so basically, wherever it changes concavity is where it had to be. So if it's positive, if it's concave up when the second derivative is positive, and if it's concave down when the second derivative is negative, then it has to switch when the second derivative is actually equal to 0, right? And so that's how it's very similar to critical points. It's just the second derivative instead. And so let's do an example. And let's do some review for this one here. So let's actually do everything that we did last Wednesday for this. So determine where f of x equal to 3x to the fourth plus 2x cubed plus, or no, minus 12x squared. Determine where this function is increasing slash decreasing and where it is concave up slash concave down. So for the increasing decreasing part of it, which I'll call A, and I'll call this part B, then what test am I going to have to use for increasing decreasing? Actually, it's not the first derivative test I want to say is actually for local mins and local maxes. So here, that's what I was thinking too. I would have said first derivative test, but I think we're really just thinking of the increasing decreasing test. Let me go back and look at the notes we took on Wednesday. Because I want to say the first derivative test is very specific to those max and mins. Where did it go? Which I didn't actually include here. Oh. Hang on. Why am I not finding my notes from, oh, there. Yeah, so increasing decreasing test is just the one we're gonna do. And then the first derivative test is the local min, local max stuff. Yeah. But so here for these notes, yeah, so here we're gonna have to find the first derivative, which since it's just a polynomial, it's just the power rule. So what is this gonna give us? 12x cubed plus 6x squared minus 24x. What can I factor out of here? 6x, yeah, I can do 6 and x at the same time. So you would get 2x squared plus x minus 4. Did I do that right? Is that how that factors? Yeah, because I would get 12x cubed plus 6x squared minus 24x. Yeah, so that's right. And so now I want to find the critical points. And so remember, this is the one I forgot on Wednesday, but it's where the derivative is equal to 0 and where else? Where the derivative is what? Undefined, yeah, or yeah, does not exist. And so here, is it ever undefined? It's a polynomial, so yeah, no, never undefined, so that's fine. But then here, what I'm going to have is I'm going to have 6x equals 0, but I'm also going to have 2x squared plus x minus 4 equals 0. Because what I'm doing is I'm just bringing this down here, right? And then using the zero product property. And so here, x equals 0. How does 2x squared plus x minus 4 factor? What can I use if I don't know how it factors? Oh, I don't know who this is. But yeah, what can I do? Yeah, the quadratic formula, right? And so actually, let me put this on do not disturb. Oh, but my phone's open, so it's not gonna matter. Okay, so quadratic formula, what is it? Negative b, so -1 plus or minus the square root of b squared minus 4 times a times c all over 2a. Okay. Okay, and then so here, did anybody solve this yet? Did anybody get the answer? Is this actually, no, this isn't going to be imaginary. This is going to be 16, 32, 33. No. Calculator. Oh. Okay. Okay, so 4 times 2 times 4. Yeah, so 33. Oh man, this is going to be ugly. So you get x is equal to -1 plus the square root of 33 divided by 4, and x is equal, oops, to -1 minus the square root of 33 divided by 4. And so here, what is the square root of 33? I didn't realize this was going to be so ugly. So this one's -1 plus 5.74, x is equal to -6.74 over 4. Are you guys getting the same things as me, or am I just doing this all wrong? Okay. 6.74 divided by 4 is -1.685. And remember, it doesn't have to be exact because you're just testing around these points, right? And so here, you're going to get 4.74 divided by 4, it should be 1 point something, 1.185. Okay. That was a lot longer than I expected, and I did not want to do the quadratic formula, but that's okay. All right, so here's the problem so far, right? And so for the increasing, decreasing test, I'm gonna move this all over. I just need to test some values around it. So increasing / decreasing test. Oops. And so how do I start this test again? What's the very, like after I find the critical points, what am I gonna do? Yeah, I'm gonna draw that number line. And so here, and then I'm just gonna put the points. So our critical values were this 0 up here that we solved forever ago, this 1.185 and this -1.685. And so really, I'm just gonna test simple numbers. And so I'm gonna have -1.685, 0, and then 1.185. And so I'll test numbers like -1, +1, 2, and -2. And so I'm gonna have to test those 4 numbers. Does everybody remember this from last week? Okay. When I, what's it called? Yeah, so that's why I wanted to review this, right? So if I test x equals -2 first, am I gonna plug in f of -2, or am I gonna find f prime of -2? Which one am I looking for here? Yeah, f prime, right? Because the increasing decreasing test says when the derivative is positive, you're increasing, and when your derivative is negative, you're decreasing. And so here, I want to see if f prime of -2, excuse me, is positive or negative. And so I'm going to take that and plug it into the derivative. And so my derivative was this guy. And so I'll have -12 times, what is that going to give me? 8 minus 2 minus 4. And all I really need to know about this is that this is negative, right? Because you're going to get -12 times 2. So this is actually -24. And so here, I'm decreasing. from, where does this interval start? Actually, it should be this bracket. Negative infinity. Yeah, so that's the first one where we're decreasing. So decreasing, we have negative infinity to negative 1.685. That's probably not the only place where it's decreasing, right? So next I'll plug in, so this is 1. Next I'll plug in x equals -1. And so again, I'm going to plug it into the derivative and I'll get -6. Where's my derivative again? -6 times 2 minus 1 minus 4. And I want to say that this is greater than 0. Yeah, so here this is positive. So now I have a spot for all my increasing answers. And so here, I'm not going to include either of those endpoints, so negative 1.685 up to 0. And so that's my second, that's the second part of my answer then. Okay, do you guys, like, are you starting to get familiar with this again? Is this seeming more familiar? Okay. Yeah, so I'm just gonna kind of finish with this. So when you test x equals 1, then you're gonna get positive 6 times 2 plus 1 minus 4, and this is negative. So this is, my next interval is from 0 to 1.185. And then here, this one's gonna start, oh wait, I have to test it. X equals 2. F prime of 2. So I'm going to get 12 times 8 plus 2 minus 4. Yeah, this is positive. So 1.185 all the way to infinity is where it's increasing. And so this right here is the answer to the first part of that question. Now we have to do the second derivative test, which I want to say is shorter. So are there any questions about any of this? I know I did that kind of quickly, especially at the end, but does this make sense to everybody? Do you have any questions? I'll leave it here. If you need to see another part of the screen, let me know, but I'm gonna leave it here for like another minute or like 30 seconds. Real quick, are you guys actually taking notes, or are you just like watching me do this and planning on working through it later? Okay, okay, good. Yeah, taking notes, like when you write it down, that's what really, it can really help. Okay, good, I'm glad. Oh, okay. Can I scroll? Does everybody have this? Okay. So then now, let's talk about the second derivative test. So the second derivative test is almost the exact same thing as the first derivative test. It tells you where you have local mins and local maxes. And so if I don't specify which test to use, then you can determine where the local extreme values are using either one. So the first part says, okay. First, you kind of have to assume that the second derivative is nice and continuous, right? So suppose the second derivative is continuous near C, where C is just some value. Then the first part says that if f prime of c, so if the first derivative evaluated at c is equal to 0, and your second derivative at that same value of c is positive, then f is going to have a local maximum, no, I'm sorry, I mean minimum value at c. Let's see. And then it has a local maximum if almost everything about that first sentence stays the same, but I'm just going to change this to less than 0, right? And so here, if the first derivative evaluated at c equals 0 and the second derivative evaluated at c is negative, then f has a local maximum at c. Oh man, I just realized we didn't even finish the example. I started talking about the second derivative test, but we needed to use the concavity test here. So I'm going to move this real quick. Or you know what? Yeah, hang on. I'm going to move this. And then we'll do the concavity test for this example. I'm sorry, you guys. But yeah, that's the second derivative test. But here, let's go back up to this example. So I'm going to write down the function again. And so I'm actually just going to copy it. So there's the function. We found the first derivative, but now we're going to need to use that to find the second derivative. So the second derivative is, again, it's just a polynomial. So I'm going to have, oh, what's 12 times 3? 36? Is that right? Yeah. Plus 12x, thank you, minus 24. And what can I factor out of this one? 12, yeah, and I can't take an x out, but I can take that 12 out. And so I can have that this is 12 times 3x squared plus x minus 2. And I know how this one factors. I have it written down, give me a sec. 12 times 3x minus 2 times x plus 1. So that one does factor nicely. I'm just going to keep moving this down. We'll get to it. And then so here, the inflection points, I'm going to have to test around those. Same way that I tested around the critical points here, right? And so the inflection points are going to be where the second derivative equals 0. And so you get 12, 3x minus 2x plus 1 equals 0. 12 cannot equal 0, so that's nothing. And then you get 3x minus 2 equals 0, and x plus 1 equals 0. And so really what you're getting is 3x equals 2, so x equals 2/3, and here x is equal to -1. And so I'm going to do something very similarly to when I did the increasing decreasing test, right? I'm going to have this line here, and I'm going to put my inflection points on it. And so I have -1, and I have 2/3. And so I basically just need to test 3 points now. I need to test a point here, a point here, and a point here. And if it's positive, it's concave up on that interval, and if it's negative, it's concave down on that interval. And so here, the first point that I'm going to test is we'll have x equals -2. And what function am I going to plug it into this time? F prime, or f double prime? Yeah, f double prime. And so I'm going to have f double prime of -2. And here, let me see. I think I have the answers to these ones. The first part of this example, I just kind of winged. Oh, you know what? Did I factor that correctly? I did, right? Yeah, I did. But so here, when you plug in f double prime of -2, you get that it's positive. And so you guys can double check me on this later if you want, but this interval is positive. When I plug in x equals, oh yeah, I can just use 0 here. When you can use 0, use 0. It's always the easiest thing to use. Then you get that f double prime of 0 is actually negative. And so I'm concave down on that interval. And then the third point I'm going to test, I can just do x equals 1 because 2/3 is smaller than 1. And so the second derivative evaluated at f is, or evaluated at 1 is positive. And so here, hang on real quick, I'm just going to move this again. And so here you get that it's concave up. Where does it start being concave up? Yeah, negative infinity up to -1. And then I can union it with this last one. And then it's concave down, basically just in the middle, from -1 to 2/3. Okay, so yeah, now that we've gone back and done the first example we were supposed to do you guys have any questions about this? So this is the concavity portion of it. Does that make sense? Does everybody see how that's very similar to the increasing decreasing test that we had done? Yeah, it's almost the exact same thing, just with a different derivative, right? And it tells you different things. All right, so I'll leave this here for a few more seconds, just so that you can write this all down. All right, so now let's get back to the second derivative test. So yeah, that's what the second derivative test says. Basically just if your second derivative is positive, then you have a local min. If your second derivative is negative, you have a local max. And the first derivative has to equal 0 at the same time. So now let's do an example. Oops. So let's look at the function f of x equals -x to the 4th plus 6x squared minus 4. And let's just find all the mins and maxes. So find extreme values. Okay. So what's the very, very first thing that I need to do here? Yeah, find the first derivative. And again, it's just another polynomial, so it's just going to be the power rule. So -4x cubed plus 12x minus, oh, that 4 just actually goes away, right? Plus 0. And so that's my first derivative. And since I'm trying to use the second derivative test, am I going to need to find my critical points? Look at what the first, well, I mean, okay, I'm gonna have to find half of them, right? Because the second derivative test says to first figure out where the first derivative is equal to 0, right? So if I go back up here, I first have to figure out this part. And then once I know which values make the first derivative equal to 0, then I'm gonna go and test these points here, right? And so it starts out with first knowing where it's equal to 0. So technically, yeah, we're not finding the critical points because the critical points also include where it's undefined, right? And here we don't care about where it's undefined, we only care about where it's equal to 0. And so what I'm gonna do is, this is what we're looking for. So I'm gonna get negative 4x cubed plus 12x equals 0, which means, so I'm going to change this a little bit so it's easier to look at. What can I factor out of this? Negative 4x. So if I take out a negative 4x, then this is positive x squared, and then this is going to be minus 3 equals 0. And so you're going to get that negative 4x equals 0 and x squared minus 3 equals 0. And so I'm going to write it like this. So you're going to get x equals 0, but then here, you're going to get that x is equal to plus or minus the square root of 3. And so if you wanted to, you can convert that square root of 3 to a decimal, but you don't have to. You can leave it like that. I'm actually just going to leave it like that because remember, when I go and I plug it into the second derivative, all I'm looking for is if it's positive or negative. I don't even need to find the exact value. And so here, now that I have figured out these points, which I'm going to need later, then I'm going to find the second derivative. And so my second derivative, that's just going to be, what is it, negative 12x squared plus 12. And so now I'm just going to take each one of these points that I found up here, and I'm going to plug them in to my second derivative. And so I'll have the first one where x is equal to 0. So you get f double prime of 0. This is equal to 12. So this is greater than 0. And so do I have a local min or a local max at x equals 0? Yeah, it's going to be a local min because it's positive. And so this one's kind of backwards, right? You would think min means that it would have been negative, but no, at least that's what I kind of think it means. So you have a local min at x equals 0. When I test x is equal to positive square root 3, when you plug it into the second derivative, you end up getting negative 24. You can double check me later if you want. But here you get negative 24, so I have a local max here. And then when I plug in the third one, x equals negative square root 3, I get the same thing of negative 24. And so here you get f double prime negative 3 equals negative 24, so I have a local max at x equals negative square root of 3. Okay, so are there any questions about this? I'm going to draw some pictures in a second, but I want to make sure that everybody has these notes down. So I'm going to leave those up for a few more seconds. All right, so yeah, let's draw some pictures now. So does everybody have this page? Because I'm about to just completely move on from it. So is everybody done writing this down? Okay. All right, so here, let's talk about the summary, summary of our tests. And so this is going to go back, we're going to review how to graph derivatives too. So let's say I give you a function that looks like this. And so you have something here, bump there. Oh, hang on. Let me do it this way, because I want it to go through the origin right there. It's not very pretty. Okay, so let's say this is my original function, f of x. Then, what's it called? When I go and I draw the first derivative, this portion right here, so from negative infinity up to this very first part, it should be, this first derivative is what? Positive, negative, or 0? Yeah, it's gonna be positive, right? Because this is increasing. And so here, let's draw our second derivative now, or no, I mean our first derivative. I'm gonna have, so from the same value, which is something like that, I'm gonna have that this is positive. And so it's gonna be a curve that does something like that, right? And I know it doesn't look like this because it should kind of go in the same direction, right? On the x-axis. So it's gonna be going negative x this way. And so that's why I know my curve kind of does this kind of motion, if that makes sense. Like it's not doing the opposite way because it's still moving negative x. But then what is the first derivative going to be at this point right here that I just circled? Yeah, it's going to be 0. And so that's why I kind of went to the x-axis here. So I kind of skipped ahead a little bit. But so yeah, right here, I should get the point 0. And then what is it going to do afterwards? So what is it going to be doing from like this whole time? It's decreasing. So my first derivative is positive, negative, or yeah, it's going to be negative. And so, but then what's happening at this point here? What is it going to do right here? It's 0 again. Yeah. And so kind of what we have to do is we have to know, so from this point, so I'll call this A for now and I'll call that B. So from A to B, it's going to be negative the whole time, but it's going to be more negative at some points than others. And so what it's going to do is it's actually going to do this. Oops, hang on. That was bad. It's going to do something like that, where it's going to like loop back up. And the reason for that is because if you kind of look right here, it's decreasing a lot faster than it is right here. And so here it's decreasing really fast, but here it's decreasing pretty slowly, if that makes sense. And so that's why it's like less negative here than it is here. Is everybody kind of okay with that? Okay. And then, yeah, so from this point again, so I get 0 again right here. And then here, the function, it's increasing up until I get to, I don't know, I'll call this C. And so it's going to be 0 here again. And so I'm going to be positive. And then at some point, at that point C, it's going to do the same thing that it did here, but backwards, right? And so it's going to be increasing really, really fast, especially right here. Like it's increasing super fast right here, so it's super positive. Here it's still kind of increasing, but not as fast, so it's still positive, but not as positive. Here it's increasing really slowly, so it's not going to be that positive, but it's still positive. And so what I'm getting is it's positive, it's going to be really positive at some point, but then it's going to go back down to not being so positive because it starts to not increase as rapidly. And so it's going to do something like this. And then, yeah, I get that 0.0 again. And then from here, it's just negative the whole time for the rest of it because it's just going to decrease. So here, let me kind of get rid of this ugliness. But are there any questions about this? So this was negative, this is positive, and then here it's negative again. But does everybody remember graphing things like this and working with graphs like this? I mean, I think this was on your first exam. Yeah. But so now let's kind of relate it to, so this is just the first derivative test. We're going to draw the second derivative in a second. But let's just kind of see how these two pictures really show that our tests work, right? And so what we're going to be doing is, so here, is this a local min or a local max? I know that's an easy question. Yeah, it's a local max. And the first derivative test that the first derivative test says, so here, let's write it down real quick. So first derivative test says f of x should have a local max when what happens? So what does it need to change from? It needs to start out at being something and then change to something else, which is a weird way of wording that question, but yeah, from positive to negative, right? So when the first derivative goes from being positive to negative, you should have a local max. And so if I look at my first derivative, it goes from being positive to negative. So right here, I should have a local max, and that's exactly what I have. So does that kind of help see, can you guys see the tests now a little bit easier? And so here, same thing, local min. And that's going to be where it switches from positive to negative. So here, when I put local max, I say, I'm really talking about f right there. And so here, f is going to have a local min because I went from being negative to positive. Does this make sense? Do these pictures help? Okay. Okay. Last kind of note about this. What are the x-intercepts called on this graph? They have a very special name. Yeah, these are the critical points, right? So the x-intercepts of your first derivative are the critical points. Okay. So now let's draw the second derivative. And so here, oh, we only have a few minutes left. So here, to draw the second derivative, here I'll use red. Now, I don't need to look at the graph of f, right? I can just kind of think of the second derivative as the derivative of f prime. And so I can just look at this graph here. And so everything in blue, everything that I wrote in blue is for f. So blue is for f of x, green is for f prime, and then red is going to be for f double prime. And so here, my second derivative, is that going to be Oh, here, this should be in green then, if what I just wrote down is true. But when I look at my first derivative, and I look at this portion right here, I'm not asking if it's positive or negative. I kind of want to see, is it increasing or decreasing here? So with this red part, is this going to be increasing or decreasing? Yeah, it's decreasing, which means the derivative of this portion of this graph is going to be negative, right? So right here, this is negative. And so when I graph my second derivative, and again, since I'm changing from negative to positive, right, because this is going to be increasing. Yeah. Well, hang on. It's decreasing here, right? And so it's actually not stopping at the critical point. It's decreasing until it gets to this like local min here again. And so I just drew my arrow wrong. Yeah, and then it's increasing. So this point right here is going to be what? What am I going to have for my second derivative? This one right here. Yeah, so it's going to be 0. And so I'm going to have 0 here. And then everything to the left of that point is going to be negative. And so it's going to do that. Okay, now that we've got that settled. And then yeah, here it's increasing until I get to this local max. And so again, I have that it's going to be 0 there. And so I have 0 like here. And it's doing that same thing, right? So it's increasing really, really fast. It starts to kind of, it's still increasing, but it's not increasing as fast, which means its derivative is not going to be as positive. And so it's all going to be positive, but some is just going to be more positive than others. And so I'm going to have a loop that looks like that. Where this is negative, this is positive, and then what is it doing for the rest of the graph? Increasing or decreasing? Yeah, it's decreasing, which means it should be negative everywhere else. And so, yeah, this is what's happening. What are the x-intercepts on this graph called? Yeah, these are the inflection points now. And so if I look, let me finish writing this down. But if I look at what the concavity test says, then the concavity test says, oops, hang on, what just happened? Hang on, sorry, one of my screens just kind of did something weird. Okay, but yeah, so the concavity test basically says wherever the first derivative is 0, right? Or no, that's the second derivative test. The concavity test just says, if I go way back up here, wherever it's positive, then you're going to be concave up, and wherever the second derivative is negative, you're going to be concave down. And so if I go back down here real quick, then from, I don't know, what is this point A? Is this A? No. This was point A right here. And so this is an A, but basically I should be concave down on this interval and then concave up everywhere here. And if you kind of bring that back up, so yeah, I'm concave up right here. And so here, I'll put this in red, concave up because it's positive, right? And then concave down because this is where it's negative. You guys see that? And then here, this is going to be concave down again. Do these pictures, like, are these helping? Does this make sense now? And so here, I'll kind of put it down here too. So concave down, concave up, and then yeah, concave down again. Okay. All right, this got annotated way more than I expected it to. But yeah, so there's more to this section, like, and I'm all kind of determined if we're gonna actually cover it or not, but the next part would be using all of these properties to graph functions. And so we might do that next time, or we might just move on to 4.5. I'm not sure yet. But does everything we talked about make sense today? I want to say part of this is on your quiz. Okay. So yeah, that's it for today. I don't know if I have any real announcements to make. I still don't know as far as the class goes. Actually, I'm gonna stop recording this now because I'm not talking about the class anymore, or about the notes. So I'll stop recording. Oh no, I don't know.